Hello everyone. Today we're looking at triangle bisectors part 2. So first off, like last time, we're going to start off with our perpendicular bisectors as well as this new term, circumcenter. Not circumference, circumcenter. So perpendicular bisectors, as covered in lesson 1.3, are any segments, lines, or planes that intersect with a segment at its midpoint, which in turn forms two congruent segments. And if it intersects at a perpendicular angle, it is called a perpendicular bisector. We talked a little bit previously about the perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. That is to say that if, in fact, these two are congruent, then CD is our perpendicular bisector, and C is the same distance from A as it is from B. The converse of this is also true. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. That is to say that if we have AE and EB being the same measurement, then CD, by definition of being equidistant from both points A and B, would be our perpendicular bisector. Now, a triangle has three sides, which means it has three possible perpendicular bisectors. These bisectors are all concurrent lines. The point of congruency of perpendicular bisectors are known as the circumcenter of the triangle, functionally the point where they all intersect. Now, the circumcenter theorem. The perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. That is to say that at the point P here, which is formed by the intersection of these three perpendicular bisectors, point P is equidistant from the vertex A, the vertex B, and the vertex C, such that PB has the same measurement as PA and the same measurement as PC. So, perpendicular bisectors form a point that is equidistant from each angle of the triangle. So, given that point P is the circumcenter of ABC, list any segments that are congruent to each segment. So, BR, segment BR here, well, BR, if P is the circumcenter, then BP is a perpendicular bisector, which means that BR is congruent to RA. Segment CS. So segment CS here, if P is the circumcenter, then SP is our perpendicular bisector. If SP is a perpendicular bisector, then AC is bisected in half, meaning that SC is the same as SA. Finally, BP. Oop, not that one. BP. If point P is the circumcenter of triangle ABC, then point P is equidistant from each vertex of this triangle. So segment BP has the same measurement as PA and PC. All right. With regard to angle bisectors, we're going to have the same sort of idea here, except this time with angles. So angle bisectors were last talked about in lesson 1.4, back in unit 1. Angle bisectors divide an angle into two congruent angles. Angle bisectors can be a line, a segment, or a ray, such that given the angle ABC, BD is the bisector of the angle, making ABD and DBC congruent angles to each other. our angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the sides of the angle. That is to say that if we have a ray BF bisecting angle DBE, then the distance of DF is equal to the distance of FE. The converse of this is also true. If DF and EF have the same measurement, then BF must be our angle bisector of the angle DBE. But angle bisectors don't form circumcenters, they form incenters. The incenter is going to be the continuation and intersection of all of the angle bisectors at some point. And this point here, P, the incenter P, is going to be equidistant from the sides of the triangle. That is to say that if P is the incenter of a triangle formed by the angle bisectors of AP, PB, and PC, then the distance from P to each of the sides, PE, PD, PF, are all going to be equal. So let's apply this. Given this figure, point A is our incenter. We want to find each measurement. So the measurement of ARU, so if A is our incenter, that means that AR is our angular bisector. If AR is our angle bisector, then ARK has to have the same measurement as ARU, because angle R would be bisected by the ray AR, which means that the measurement of ARU would be the same measurement ARU would equal ARK, which is equal to 40 degrees. The measurement of AU in number 11, so AU, well, AU, if point A is the incenter of PQR, then AU is the distance between the incenter and one of the sides, which means it's the same distance as AK and AT. So AU is equal to AK and AT. Angle QPA, so QPA, well, QPA is a bisected angle from the bisector PA, which means that this 3x plus 2 must be equal to this 4x minus 9. So we're going to set up our equation as 3x plus 2 is equal to 4x minus 9. To solve for x, we're going to move those x's over. We'll end up with x there. Move that 9 over. We get 11 is equal to x. So find the measurement of angle PQA. Well, sorry, QPA. So QPA is 3x plus 2, which is 33 plus 2, which is 35 degrees. Measurement of QA. Well, let's see, measurement of QA. So QA is the distance from our incenter to the angle Q. But our incenters don't give us any information about the distance between the point in the center and the angle on the outside. This is an angle bisector, certainly. We don't know the measurement here. We don't know the distance, because it's the circumcenter that gives us the relationship between the vertices and the inner point. So what is a measurement of QA? Well, we have no information for this, so we will just put not applicable. And that, folks, is part 2 of the notes. We will have an assignment on this, assignments on this tomorrow, Thursday, and Friday. Please ask if you have any questions.